So now we're going to continue our discussion of linear regression and fitting models with an example related to data from the Galapagos Islands. So there's a data set in the faraway package called gala for Galapagos, and this data set has the number of species of tortoise on the various Galapagos Islands. And so we have 30 cases, or islands in this case, and there's actually 7 variables, though we won't use them all. So the response is going to be species, which is the number of tortoise species found on the island. Area, which is how large the area is in kilometers squared. The elevation of the highest point on the island in meters. We're also going to look at the nearest variable, which is the distance to the nearest island, also in kilometers. S cruise, which is the distance from Santa Cruz Island, which I think is the main island in the chain. And then how large the adjacent island is. So this one is also the nearest in kilometers squared. And so we have our response, and we're going to have 5 predictor variables. And we want to use these variables to construct a model for species. So let's go to R and actually start looking through this. So the first thing we need to do is we need to load the data set, which is in our faraway package. So we use the data function, we specify the name of the data set we want, and then we specify where the data is located. The reason that, well, there's different ways of doing this. So if you have already loaded the faraway package, you can just type data gala. But since we haven't actually done that in this particular set of code yet, we want to specify where the data is located, and it's in the faraway package. So we run that line of code to obtain our data set. And then it's always a good idea to use the head function to look at the data, just to get an idea of what it is. And the reason that we have this -2 here is because we do not need the second column, that second variable, which we're not going to use. So I'm just removing it before we look at the data for simplicity. All right, so here's our data set. And so we have the name of the different islands here, so Baltra, Bartolome, Caldwell, Champion, etc. Then we have our response and the 5 different predictor variables. And now we want to fit our linear model. And I've already alluded to this in class, but the most important function that we're going to use throughout the entire semester is this LM function, which stands for linear model. And with the LM function, you really just need to specify the response variable, and then this tilde means regress on. So we're regressing species on the variables on the right-hand side. And what we do here is we just add the variables that we want to regress the response on. So we want the area variable, the elevation variable, the nearest variable, and the S cruise variable, and I guess the adjacent variable. And a lot of times when we're doing this, our data is actually going to be stored in a data frame. So these are not vectors that are stored in R's memory. And so if these variables are stored in a data frame, then we specify data equals gala, just like we did with the plot function. And what this lets R know is that when we want to construct these models, or this model, it should look in this data frame to obtain the variables of interest. So we run that command, the lm function, and we store the object that's produced in the lmod object. So where we stored our linear model is in lm. And then now I am going to load the faraway package because there's sort of a nice little function that the author provides to view the results called summary. But notice it's actually spelled wrong. So you can do the same thing with 2 m's. It just gives you more output. So we're going to use summary with only a single m and look at the output here. And this gives us quite a bit of information that's going to be useful to us. Okay, so this first column right here that says estimate, these are the estimated regression coefficient for each of these predictor variables in our model. So the coefficient that's associated with the intercept variable, or within the intercept, is estimated to be 7.07. The regression coefficient associated with the area predictor variable is -0.02. The coefficient associated with the elevation variable is 0.32, etc. So standard error is the standard error of our estimate. So essentially this is a way of quantifying how much uncertainty or error is associated with each of these estimates. The t-value here is a test statistic that we can use for hypothesis testing. So we'll learn more about this in the next chapter, actually, or maybe it's 2 chapters from now, but when we're talking about inference. But if you want to do a hypothesis test related to a regression coefficient, if you want to test that it's equal to 0, the test statistic that you would use is just the estimated test statistic over the estimated standard error. And so that's what's computed in that column. That t-value column is the test statistic, which is just the estimate divided by the standard error. And we can do that for all of the predictor variables in our model. And then this last column, the probability greater than absolute value of t, is actually the two-tailed p-value for this particular hypothesis test. So at this point, you don't need to really know how to understand these last 2 columns beyond the fact that there is a test statistic and a p-value for a certain hypothesis test. And we'll learn the details about that later. So sometimes you don't want to look at all the information, right? So this is a lot of information. Sometimes we just want to look at the coefficients. And so after you fit your linear model, you can simply run the COEF function on your linear model, so coefficients on L mod, and that will extract the coefficients that you have fit. So once again, we have our estimated coefficients. They're output in a vector here. So some questions for you guys. So what I want you guys to do is, once again, pause this video, and then I want you to try to answer these questions on your own. So take a few minutes and do that. You want to find the equation for the fitted model. You want to find the fitted value for the first observation, so y hat. And then you also want to find the residual for the first observation, which is just the fitted value minus the first response. And we've already gone through enough information that you can compute these if you know where to look. So why don't you take a few minutes, see if you can't find the answer to, or answer these questions, and then we'll look at the solution together as a class. Well, I hope that exercise went well and that you felt successful in finding these solutions. But let's just look at the answers together just to make sure that we're all on the same page. So the first thing that we want to do is find the fitted model. Okay, so the equation for the fitted model. So the fitted model, and as I've said before, we usually just use the notation y hat here. So what's the equation for the fitted model? Well, it's the estimated intercept plus the linear combination of each predictor multiplied by the estimated coefficient. So you're going to get minus 0.02 times area plus 0.32 times elevation plus 0.009 times the nearest predictor variable minus 0.24 times S cruise, and then lastly minus 0.075 times the adjacent variable. And just to be sure that you guys know where I got this from, we'll go back to our output here. And so I have this column here with all the estimates. And so for each of these different predictors, I'm just going to multiply the predictor variable by the associated estimated coefficient, and then also including the intercept in there. Okay, so that's where I got my fitted model from. And for the next step, we needed to obtain the fitted value for the first observation. And so you may be wondering, well, how did I get the information for the first observation? Well, that's what we did actually when we looked at the head function. So head of gala, we looked at the data for all the observations and not all the observations, but the first 6 observations and each of the predictors and response variable here. And so we can see that for the first observation, the area was 25.09, elevation was 346, nearest is 0.6, S cruise is 0.6, and the adjacent variable is 1.84. And so to obtain the first fitted value, I'm just going to take each of these numbers, I plug it into my fitted model, and I'm going to compute the result. So the first fitted value, so y hat 1 is going to be 7.07 minus 0.02 times 25.09. And I'm rounding a lot here. You shouldn't actually be doing that in the computation, but I'm writing out the rounded result for simplicity. So plus 0.32 times 346 plus 0.009 times 0.6 minus 0.24 times 0.6 minus 0.075 times 1.84. Okay, so now I just need to compute that. And if you do this, you should get some number close to 117. Though if we didn't round, we would actually get 116.726. Okay, there's actually still a little bit of rounding there, but it's not rounded until the final step. So the fitted value for the first observation is 116.726. And now that we have that, we can obtain the residual for the first observation, so epsilon 1 hat, which is just y1 minus the fitted value. And if we go back to our data set, or output here, we see that the response for the first observation was 58. And I'm going to subtract from that the fitted value for the first observation. So I'll subtract 116.726, and I get negative 58.726, which is actually a pretty large residual. It's basically just as large as the observation. So I'm not sure if this fitted model is actually very good at this point, but I wanted to make sure that we went through these computations just so you guys understood where these numbers are coming from. And I realized here I forgot to do the subscript there for y1 minus y1 hat. So we computed the fitted line, the fitted model here, have that, and then we computed the first fitted value by plugging in the information for the first observation, and then we use that to obtain the first residual. And you'll be asking yourself if there's easier ways to do this, and the answer is yes. And so let's just talk a little bit more about the computations that we can do in R. So one of the things that's good to be able to do is to do these computations manually. So in other words, if you didn't have R to automatically do this for you, would you be able to fit the results or obtain these results on your own? And so what we're going to do here is we're going to look at how to compute this just using basic matrix algebra. So to do that, we need to obtain our x and our y, right? Because what we need to do is we need to get our estimated coefficients, we need to obtain x transpose x and x transpose y. So we need our x and we need our y. And so how do we get our x matrix? Well, I'm going to cheat a little bit. So you could just create these using the matrix argument or the matrix function or the c-bind function. We're going to take a little bit of a shortcut just because it's a lot more straightforward. And that's going to be using the model.matrix function. So with the model.matrix function, you give it a data frame in this case. So we're going to give it the gala data frame where our information is stored. And then you just provide the right-hand side of the formula that we used to fit our linear model. So what we're saying is that we want to construct a regression model that has area, elevation, nearest, S-screws, and adjacent as predictive variables. And then this will go through the process of computing the x matrix, returning it, and then we're just going to store it in an object named x. And similarly, I'm going to obtain my y variable, though it's a lot more straightforward there. I just need to get the species predictor from the gala data frame. So use that $sign operator to extract the species vector from the gala data frame. I'm going to store it in an object named y. And up to this point, we have not really introduced how to do matrix algebra in R. So I'm going to give you guys a brief tutorial about some of the operations that you can do. So transpose is very important, and unlike MATLAB where you can use a prime or something like that, the function that transposes a matrix in R is the T function. So T, and then you would provide the matrix in parentheses, and that will give the transpose of a matrix. To do matrix multiplication between two matrices, you can't just use a star symbol like in MATLAB. You actually have to surround it with these divisor symbols. So it's divisor star divisor. And so this is a special symbol that R uses to notate matrix multiplication. And unlike MATLAB, there's not an inverse function in R. because that's actually a really bad idea for various computational reasons. So instead, you have to use the solve function. And what solve a comma b does is it calculates a inverse of b. And so you actually have to kind of think about what you want beforehand, and then put the matrices in the correct order to get what you want in the end. Okay, so those are really the three functions, matrix functions, that we need to know in order to compute or to estimate the regression coefficients using matrix multiplication in R. So I need to compute x transpose x inverse x transpose y. And so I need the transpose of x, so I use that t function on my x matrix. And I want to multiply that using this symbol by the x matrix. And I want to take the inverse of this whole thing, right? Which means that I need to provide that as an argument in the left-hand part of the solve function. So going back to the previous slide here, okay, solve AB is A inverse B. So if we want x transpose x inverse times x transpose y, then A is going to be x transpose x, B is going to be x transpose y, which is what I'm doing on this next slide here. So this is x transpose x, and this is the transpose of x multiplied by y, and then the solve of that is going to be x transpose x inverse multiplied by y. And so if I actually do that in R, this is what I get out. And if you compare these to the output that we already obtained, you'll see that the results are identical. So we have obtained the estimated regression coefficients just using straight matrix algebra in R. So this is a nice little thing to be able to do. Though I want to point out a few different things. So this is not something that is going to be important for most of you, but if you're doing lots of matrix calculations in R, it's important to know how to do things the right way. So actually using the transpose function is not a very good way of doing things in R, because R actually internally computes the transpose, and then when we multiply it, then it does the matrix multiplication. There's actually a function that does both at the same time. So instead of actually transposing the matrix and then multiplying it by what's on the right-hand side, it just knows how to multiply it in the appropriate way. So it doesn't actually take the transpose, so it's a little faster. And that function is the cross prod function. So cross prod of x comma y calculates x transpose y, and that's actually a better way of computing x transpose y, for example. And as just sort of a shortcut here, you can do the same thing. We also want x transpose x, but if you just give it a single argument here, then it just assumes you want x transpose of the argument itself, which means that if we want x transpose x, we can just do cross product of x. If we want x transpose y, we can just do cross product of x comma y. We put those into the solve function, and we obtain the same results. And this is not going to seem any faster to you or anything like that, but I promise you that it is actually faster under the hood. It's just that it's so fast that we can't see it with our eyes. But if we actually time these, then the second way would be slightly faster than the first. So we can compute these things by hand, but it seems like it'd be really great if we could extract some of these quantities automatically from R. So is there functionality for doing that? And the answer is yes. So there's a variety of functions that we can actually use to obtain information directly from the fitted linear model. So if you want the residuals from your fitted linear model, you just use the residuals function on your fitted object. If you want the fitted values, then you would just use the fitted function on your fitted linear model. If you want to know the residual degrees of freedom, which we haven't really talked about a lot yet, you could use the df.residual function on your linear model. If you want the residual sums of squares, if you want to extract that automatically, you can actually use the deviance function on your fitted linear model. And there's actually other functions and other things that you can extract from the linear model. If you use the str function or the names functions on your fitted linear model, then you can see some of those. Okay, so here we have, so basically this is showing you what is stored in your linear model fit. So you can see we have coefficients, we have residuals, the fitted values, the residual degrees of freedom. The model is actually the formula that you use, and then there's some other things which we don't really need to talk about at this point, but could be useful depending on what you're trying to do. And then if we if you use names on the summary function, okay, so the summary function is going to provide more information about what's in LMOD. You can see what's stored in there. There's also some additional information. So we get the residuals here, still the coefficients. Sigma is sigma hat, which is the square root of sigma hat squared. So this is the estimated standard deviation of our errors. the adjusted r squared, the r squared values, the degrees of freedom. And so there's lots of information that you can actually pull out from these fitted linear model objects. You just have to know how to obtain them. And so we will, of course, talk about the ones that are going to be useful as we progress through the semester. So let's look a bit more about some of the things that we can do with this. So I'm just going to walk through this code that we've sort of already done here, but I'm extracting my x matrix and my y matrix, and then I'm fitting the two, or I'm estimating the regression coefficients just using the regular old matrix algebra. You see the same results that we got before. And then here's looking at some of the things that you can obtain from within the fitted linear model object or from a summary of the linear model object. Okay, so both of them are useful. So let's say that we wanted to estimate sigma, so we can obtain that from L mod sum, so we can see that right here, right? So L mod sum contains sigma, so this is just sigma hat. If we run that, we see the value is 60.975. But, in fact, we'll go over here. So we've already learned that sigma hat squared is the residual sums of squares divided by n minus the number of regression coefficients in our model. And in our notation, not our notation, but the notation of R, the software, RSS is obtained from the deviance function. Okay, and n minus p is just going to be the residual degrees of freedom. Okay, and if we want sigma hat, then we just need to take the square root of that right there. And so that's what we're going to do in the R code here. So the deviance divided by the residual degrees of freedom, we take the square root of the whole thing, and we get the exact same number. Or manually, I could instead do so the residual sums of squares is actually the sum of the squared residuals, right? And so another option is that I can sum the squared residuals and then divide it by the residual degrees of freedom, which is what I'm doing in this last step. So there's actually even more ways of doing this, but a few different options for you. So I'm taking the residuals from my model. Okay, that's the residuals function will get the residuals. I'm squaring each residual, and then I'm adding it together. Okay, so I'm just going to run that part. Oops, I need a closing parenthesis here, which I can, or sorry, the residual sums of squares, which I can also obtain from the deviance function. Okay, get the exact same numbers here. So I can sum the squared residuals, I can divide by the residual degrees of freedom, and then I take the square root of everything in order to obtain my estimate of sigma. Okay, so sigma hat is once again 60.975. So yeah, so we can obtain sigma hat, which is great. So another quantity that we have talked about is that estimated standard error. So the variance of beta hat is sigma hat squared times x transpose x inverse, and then the standard error is just the diagonal. The estimated standard error is just the diagonal matrix of that. Okay, so I'm going to look at how to compute those standard errors by pulling the information directly from R. So the first thing I need to get is x transpose x inverse, and we could compute this again if we wanted, but you can actually pull this directly out of the linear model summary. So L mod sum $cove.unscaled will give me x transpose x inverse, which is nice. So x transpose x inverse, I just extracted that from L mod sum, and then I'm taking the diagonal element. So diagonal obtains the diagonal element. So I'm taking the diagonal elements of x transpose x inverse, I'm taking the square root, and then I'm multiplying them by sigma hat. Okay, so there's my standard errors. And if I just looked at the second column of output from the coefficient object of L mod sum, I'll get the standard errors, and you can see they match up exactly. Or if you wanted, if you're not sure what I'm doing here, I'm trying to extract this column from this matrix. So that's what I was doing when I extracted the second column from the COEF object from the L mod sum object. So this is the estimated standard errors, and we have calculated those sort of manually, right? So pulling out the necessary quantities and calculating them ourselves. And if we actually just wanted that V matrix, there's actually another function that you can use, the vcove function. So vcove, so I'll run that here, gives you an entire matrix, and that is giving you this matrix right here. So this is what vcove of L mod is going to give you. And so if we wanted to extract the standard errors or obtain the standard errors from that, I need to take the square root of the diagonal elements. And so you can see in my code down here, I'm going to take the covariance matrix, I'm going to extract the diagonal elements, and then I'm going to take the square root of them all. Okay, and then once again, the standard errors that we produce match what we saw in the second column of this table here. Okay, so we've computed the standard error. And there's some other stuff in here that you can do. So I'm just doing some matrix computations here. I'm not going to go into a lot of details about this. You can work through that on your own if you want. Maybe the only one I'll mention, since we haven't used it again, but is the fitted values. So if you want to obtain the fitted values, you just use a fitted function, and you can see here, this matches what we computed earlier for the first fitted value. And if we looked at the residuals instead, residuals of our linear model, you can see it matches what we computed before as well. And so there's really no reason to compute those all by hand. We can just compute those automatically in R and then extract them from the fitted linear model object. And we're done.